Hi, okay, so I'm Josh Dorrington. I'm actually at the Karlsruhe Institute of Technology, not Oxford anymore. And I'm a postdoc there working with Christian Grams. And today I'm talking about some work I'm doing in collaboration with Federico Grazzini at LMU and with Lara Ferranti, Linus Magnussen, and Frederick Vitard at ECNWF. And so I'm not part of the CAFE project, but I'm doing some work as part of the Waves to Weather. We're doing a sort of transfer project. And I think it sort of has some thematic links and continuing on from some of the great successes coming out of CAFE. And so today I'm going to be talking about a sort of tool we're developing to identify the large-scale dynamical precursors of extreme weather events. And today in particular, I'm going to be talking about extreme rainfall in North Italy as a sort of motivational case study. So I'm sure, given the audience here today, I don't have to talk about the importance of predicting extreme events well. And in Europe in particular, we know that extreme flooding and flash flooding is one of the most damaging extreme events we have, both in terms of economic impacts and loss of life. And just last week, we've had these very large floods in Italy in March, which have killed, I think, 11 people. It's the final death toll, so it's a very severe event. And of course, the earlier we can get warning that these events are going to happen, the better preparation actions people can take. And so the good news, of course, is that our forecasts are getting consistently better over time. On the left, I'm showing some measures of forecast skill in the IFS over different, okay, I'm not using that, over the last 10 years. And we can see that in a number of sort of relevant large-scale variables, the skill is getting better and better. But the sort of trade-off for that is that we're achieving that skill by, maybe it's by adding extra ensemble members, increasing model resolution, increasing the number of start dates of our model. And this is leading to an exponential increase in the amount of data we're producing and the sort of the complexity of the forecast. And so that means it becomes difficult to even download, let alone analyze the sort of vast quantities of forecast data we're producing. And so increasingly, we're ending up treating our sort of very physically meaningful models as more or less a black box. And that can be a problem because we know that there's much more value in our forecast systems than is present in the direct model output. And for one motivational example of that, I'm going to talk about this, the storm Alex, which happened in 2020. There was a huge amount of rainfall, 0.5 meter of rain in a 12-hour period that struck over the south of France and the north of Italy. And on the top left here, I'm showing from the 4-day IFS forecast, an extreme forecast index for total precipitation. So if you don't know the extreme forecast index, it's basically a measure of how far into the tail of the rainfall distribution you are in this case. And so in this 4-day forecast, you can see there's sort of some yellow, a bit of orange, and that indicates that there's a sort of higher chance than normal of having some quite heavy rainfall, but it's actually in the wrong place. It's too far to the west of sort of where the event eventually occurred, and it doesn't necessarily convey the severity of the event. However, on the right-hand side, I'm showing from the same forecast, the extreme forecast index for integrated vapor transport. And here we can see the sort of wide swath of angry orange that indicates a very large scale, sort of extreme convergence of moisture into this region. And it actually falls right over the correct sort of region where there was indeed the extreme event. And so this is sort of this large scale field. The integrated vapor transport, of course, is necessary to produce the heavy rainfall, but it's not. So the model was able to get that far, but then sort of stumbled at the final hurdle of actually producing the correct rainfall extreme. And so, of course, if you looked at this field, if you looked at this integrated vapor transport plot, you would probably get a sense that there was a chance of a very extreme event on the way. And so this sort of fed into sort of the motivation of this project, which is that extreme events don't just happen out of nowhere, obviously, they're associated with a story. In this particular North Italian example I'm focusing on, sometimes that story can be quite coherent and it has some quite long-range predictability. So, for example, if a cyclone extratropically transitions in the West Atlantic, that can lead to the growth of a Rossby wave packet. That Rossby wave packet can then create a trough to the west of Italy produce an atmospheric river where you've got a lot of strong northerly transport of moist Mediterranean air. And when that moist air hits the sharp orography of North Italy, then it can cause flash flooding. And so if we can sort of map out the narratives and the sort of chains of precursors that produce these extreme events, we should be able to understand them better and to predict them better. And so, of course, there's lots of sort of research in this line where people look at different extreme events and they identify the large-scale precursors, but it's normally done on a sort of case-by-case basis for a particular event in a particular location, and it's hard to sort of extend that to a more systematic approach. So, yeah, so just for sort of to be clear about what I'm talking about, in this talk, I'm focusing particularly on autumn, but we're also looking at other seasons. In autumn, the Mediterranean is very warm, and so there's a lot of cape and there's a lot of moist air, and so that's produces some really severe floods. And I'm just interested in trying to predict autumn extreme rainfall events over this Marst region in North Italy here, and I'm sort of taking a categorical perspective where on each day there either is or isn't an event based on the exceedance of a sort of rainfall threshold. And so my partner, sort of collaborator in this project, Federico Grazzini, he's focusing on taking a lot of this knowledge about the dynamical drivers of North Italian extreme rainfall, and he's been developing a sort of hybrid approach that takes the direct model output and combines it with a number of the large-scale local variables like the IVT field and putting it all into a random forest model, leveraging sort of some of the advantages of machine learning to then produce a more accurate prediction of the local rainfall. And he's sort of developing some plots that look a bit like this. So this is hot off the press. This is for this March event last week. And so here we're trying to predict rainfall at different lead times from this random forest model. So the x-axis is showing us different valid dates. So that 15th of, actually I will use this now. This is the sort of when the severe rainfall happened in March. And this is different forecasts from sort of 0 days before the event to 9 days before the event. And we could see that in this sort of random forest approach, even 7 days before the event, we had a pretty coherent story that there was going to be high rainfall over that region. So that seems to be coming along quite nicely. In my part of the project, I'm trying to develop something a bit more generalizable. And so the first thing I'm doing is I'm producing sort of composite fields of different large-scale variables to try and understand the narrative of particular events. So here I've produced composite integrated vapor transport and Z500 fields for sort of 260 Italian extreme rainfall events I have in Era 5. And so what we can see is that in the top left corner, integrated vapor transport, you get this sort of very high sort of band of moisture convergence into the region. Of course, you need that if you're going to have heavy rainfall. And then at sort of longer lead times before the event, in the bottom left here, I've got this Hofmüller diagram of Z500 over the Atlantic. And you can see that even sort of 6 days before an event happens, you start to get signs of a wave train developing and sort of on average. And looking sort of specifically in the map here on the top left, sort of 4 days before the typical North Italian rainfall extreme, you have this Rossby wave train developing, coming all the way from the west of the US. And by the time we get to the day of the event, that's sort of clarified into a deep trough that then provides those strong northerly winds that you need to get the moisture into the right location. And so the question is, can we use something like this to then sort of actually improve our predictions? And so that's what I've been working on. So I've been developing this toolkit, which I'm sort of calling Domino. And at the moment, it's just a sort of Python package. It's very much in an alpha stage, but it is up there if you want to have a look at it. And the way it works is we pass in some event definition. So in this case, it's extreme rainfall, but I've also been looking at cold wave extremes and different extreme events. You pass in some Boolean time series. You pass in a large number of different spatial fields from this sort of historical record. And first you compute these average precursor fields, like I was just showing you. And the next step is to reduce those fields down to scalar indices, which then provide sort of measures of the activity of these different large-scale precursors. And then when you have this database of scalar indices, you can use those as input into a predictive model. So just to explain how that would work, again, here I've got this IVT field. So the first thing we do is we produce the IVT composite. And then do some masking to identify only significant anomalies. Then I apply a bit of post-processing to produce a sort of clean composite. And then what I do is I've identified this pattern, and I do sort of a dot product between this pattern and every IVT field in the historical record. And then that produces me a scalar time series. So when this scalar time series is large, it means in this case that you have just such high levels of IVT over Italy and sort of low levels in the surrounding regions. And then from there, I can say, well, when that index that I've produced is in the different deciles of its distribution, how does that change the likelihood of having an extreme rainfall event? And so in this particular case, when this IVT index is in its higher deciles, the chance of an extreme event goes from sort of, it's 4 or 5 times more likely than normal. So it goes up from sort of 6% chance to 30% chance of having an event. And I can do that for many different fields. And so here I've done it for IVT and for the zonal and meridional wind, low-level winds, for equivalent potential temperature, and for CAPE. And in each case, produced a composite, turned it into a scalar time series. And then I can produce this sort of activity indices, and I can plot those up as a dashboard. So I can quickly get a summary of the current atmospheric state and how it relates to the chance of a North Italian rainfall extreme. And so in this case, for Storm Alex, I went back to that case and I saw that all 5 of these indices are in their top decile. And so even without looking at any charts, even if you just had this some sort of activity monitor, you could easily get a sense that, hey, looks like there might be quite a high chance of an extreme event coming on this particular forecast day. And you can do that for different lead times. It doesn't just have to be the day of the event. So for example, 4 days before Storm Alex, there was already quite elevated wave activity in the West Atlantic, upper decile sort of Rossby wave train activity coming across the Atlantic. And so that might also be an early warning that you could identify. And so the idea here is that the forecast models often do a very good job at the sort of large scale dynamics, but they often struggle to turn that into a subgrid scale extreme. So you can imagine, for example, using if you were monitoring the Rossby wave activity on day 10 of your forecast, then that provides you a sort of statistical predictor of the chance of a heavy rain at day 14. And so the ultimate aim is that that might then be more skillful, might be able to push the predictability horizon just a few more days into the future. So this is sort of very, very early stages. We haven't yet put this sort of into the IFS. This has all been done so far with reanalysis. But we have started combining what I've been doing with the random forest model that Federico Grazzini has been working on. So what am I showing here? On the orange line, this is showing Breyer score loss. So lower is better in this particular case. And this is saying what's the skill in predicting the probability of a rainfall extreme. And the orange line is using various local measures of sort of IVT and temperature and so on to supplement the IFS model output. And then in the blue line, we've included some of these non-local precursors, just sort of chuck them in a very naive way to see if it helps at all. And already we're seeing small but sort of marginal improvements in the predictability by including this sort of long-range, non-local perspective. So that's looking promising, and we're going to do a lot more to try and get some much more substantial skill improvements in the coming months. So challenges we're facing and working on addressing is identifying the presence of different pathways into an event. So not everything's as simple as this North Italian case where there's actually quite a clear sort of way. It's pretty much one main way that such events happen. Some extreme events can occur from many different driving pathways. And so sort of finding a way to identify that there are multiple competing pathways and then separate them out, something I'm actively working on in this tool. There are some questions about how you handle seasonality. If you include sort of more events altogether, then you get clearer results, larger sample size, but obviously in different seasons, sometimes the dynamics can be quite distinct. So there's some questions about how to balance that. And then the big question really is, how do we actually go about adding in this perspective to a probabilistic ensemble forecast in the way that maximizes the sort of added value? Since I've got a couple of minutes, yeah. And one interesting question that came up from last week, so this big storm, this big rainfall extreme in in Italy last week was partly driven by the sort of self-organized, self-sustained convection that was happening over the region. It's indicated by the sort of V shape to the rainfall. And that storm just stayed in place for many hours and sort of maintained itself. And so that's what led to it being such a major extreme event. And so it's quite an interesting question about like how dependent is that sort of mesoscale self-organization on the large scale flow? Is it predictable? Is it ultimately conditioned on what's happening on the much more predictable synoptic scale, or is it somehow a bit more ineffable? And so that's one challenge in answering that question is it's actually quite hard. There's not a clear metric to tell you that such a mesoscale convective self-organization exists. So it's not easy to build a climatology of these things. So in conclusion, we're working on developing a way of reducing a large high-dimensional forecast down to some physically understandable and event-specific scalar precursors that we can use to then understand that event and to predict it better. We're going to put these into the IFS eventually and sort of develop a prototype hybrid prediction system. And in the short term, hopefully by the end of this year, I want to be producing these sort of precursor activity plots in sort of real time based on Era 5 data and have those online for a small range of different extreme events. And that will be something that you'll be able to look at if you're interested in such things. So thanks very much, and I welcome any questions you might have. And that's the end.
For your interesting talk, we can take questions now. Yes. Hold on, there's a microphone coming.
Yeah, no, one question that was occurring to me is how you handle the spatial, at what spatial scales are you going to apply that? Because I guess depends on the spatial scales you look at. You are looking at northern Italy, but maybe eventually want to look, I don't know, at a larger region, and maybe different precursors will be significant. And how you plan to handle that? Or
so I suppose definitely, for example, one of the cases I've been looking at, which is a bit more challenging, is North American cold extremes. And there, because there is a sort of larger spatial scale, you do get these different pathways because there's events happening in different places. I guess the idea really, though, is that ultimately we'd like to have more localized information about extreme events if we can. And so one thing we're trying is sort of breaking down, like looking for cold extremes really in relatively small regions of North America in that case. And then you quickly see that there are certain quite difficult regions where two different pathways both cause an extreme, but then you'll see that sort of in the south, in the northeast, there's one pathway drives most of the events and it's a different one in the northwest. And actually you can almost gain predictability by looking on a smaller scale. So in some ways it's better to look at a more local region because there's more specific drivers of those local dynamics.
Thank you.
More questions? I have one question. In your plot about the Brier score, there is a large jump at about 5 days, right? Which probably is expected at some point. Do you think you can improve this plot by using seasonal patterns instead of overall annual patterns?
Instead of?
I guess you didn't take into account seasonality here, right? Of the patterns.
This does account for seasonality.
This has seasonality.
Yeah. So okay. This is based on this is just a plot for autumn. Yeah. Just for simplicity of presentation. I think the big jump 5 days here is largely because a lot of the precursor signals I detect, they go out to sort of day 5, and beyond that, they become a bit less significant. And so what I'm doing here is we're supplementing the forecast with, imagine you're making your forecast 3 days beforehand, then you already have those day 3 precursors in observations already, but at day 6, you don't have them yet. And because I haven't computed these precursors in the forecast data yet, we can't say, look at the precursor activity in the forecast itself at day 2 of the forecast and then use that to project ahead. So I'm thinking that, so basically what's happening is we're supplementing the first sort of 5 days or so with some extra statistical data, and that's not being used as much at the longer lead times. But hopefully once we've advanced this a bit more, that benefit should push out a few more days.
Thank you.
Does that make sense?
Yes, yes.
So, okay, works. Thank you for the presentation. I would like to know, how did you convert actually these composite fields into univariate time series, or like multiple univariate time series?
Yeah. So if you, so say we've got a composite, okay, in the top left, and then we sort of mask it based on a sort of bootstrap significance test to find where the anomalies are significant. And then what I do is I sort of apply a filter that gets rid of small numbers of isolated grid points. That's sort of not very helpful. And then I apply a sort of a convolution to create a smoother edge to the composite. And so I end up with a pattern like in this bottom here. And so we take only the unmasked grid points and do a dot product between IVT anomalies at every day and that pattern. So it's essentially like a projection onto that pattern. And then I sort of standardize the time series over a reference period. And so that produces my index. Does that make sense?
Yeah, yeah, that makes sense. Thanks.
One last quick question. Okay, so let's thank the speaker again.